So we've been talking about magnetic fields. Magnetic fields can be a lot of fun. You have two magnets, they attract each other, they repel each other. But can they be useful? Yes. Yes, they can, and you've used it multiple times today. Faraday's law is what makes magnetic fields useful in modern society. In fact, it's what's made modern society possible. I shall explain more in a little while. But first we need to define magnetic flux. So magnetic flux is the magnetic field through a loop. We had electric flux before. It was the electric field through a surface. So this is the magnetic field through a surface. Usually it's going to be a coil of wire, so that's why I use the word loop. So we use the same symbol for flux. This is capital Greek letter phi. Just put a B subscript on it for magnetic flux as opposed to electric, but it's the integral of B dot dA. And this would apply in general. So if the magnetic field is different at different points on the loop, wherever it was, or if it was a changing direction. But most of the time, this is going to be a nice flat loop. It's going to be a circle or a square, not a sphere or a cube, a circle or a square. Nice and simple. So most of the time, this is going to be given by BA cosine theta. So the strength of the field, the area of the loop, and then the cosine of the angle between B and the normal to the loop. So units. Magnetic field, you know, is measured in Tesla. Area is in meters squared. Cosine is just a pure number. So magnetic flux does have a unit, and it's called the Weber. Symbol is WB. So Webers are the measurement of magnetic flux. Why when they went to the trouble of naming it, I don't know. There's not an equivalent name for electric flux. Electric flux was just, let's see, electric field, newtons per coulomb times meter squared. It didn't have a special name, but magnetic flux does. So, for example, if we have a magnetic field across the page, and we have a flat loop of wire, then there is no flux through this loop because the magnetic field lines would skim over it or go underneath it. This is, you know, infinitely thin. Or anything that came in that like goes out. No, that's not a good way to say it. It goes over or below. And that's because this angle would be 90 degrees because the angle is between the magnetic field and the normal to the loop. So the loop's material is here. It's flat on the paper. The normal of that is perpendicular, either out of the page or into the page. Well, if I do into the page a magnetic field, you can see that's a perpendicular line. Perpendicular angle, excuse me. So the flux equals 0. If we turn this loop, so we've got this circle and we're going to turn it perpendicular to the field, the plane of the loop is perpendicular to the field, so it would look like this. Well, now this angle is 0 degrees, and we would have the max flux possible through that loop. If you're at halfway, I'm not even going to attempt to draw that. But right here, because the loop is like this, the normal to the loop is this way. Magnetic field's also this way. And that's a cosine of 0 degrees. Now, if you were to flip this loop over, by the way, you would need to leave the normal in the same direction. So if you choose to make the normal this way, because you have a choice, normal means perpendicular. So if the loop is here, then normal is either this way or this way. Let's say it's this way. And now let's turn the loop over. You've got to leave the normal on the same original orientation. So if I flip the loop over, now my normal is this way, and then your angle would be 180. That's going to be important in a little while. So now we can talk about why this is important and work up to Faraday's law. If you have a magnetic flux through a loop, whatever, that's fine. But if you change the flux through the loop, that's when things get interesting. So that's when we come with Faraday's law. We have an induced EMF if the flux is changed. Now, induced meaning we're making one from it looks like nowhere, though that's not nowhere. EMF, remember, is the same thing as potential, or voltage. So we are inducing a voltage, but only if the flux is changed. So here's the actual equation. E equals negative d delta B, or d flux dt. So here is the main thing. Yes, of course you need to know flux too, but here's the main Faraday's law. So let's talk about a couple of pieces. One, the EMF is induced in the opposite direction of the change. That is going to be something we're going to handle separately. So for today, you're really going to do absolute value. Nothing's going to be negative. Then we have derivative, so that's the time rate of change of the flux. So we can change this 3 different ways. So this happens if we change the strength of B, if we change somehow the area, A, or if we change the angle. That is actually the most common, because we can rotate the loop. It's actually what this is leaning up to here. If we took this loop from here to here, we've changed the flux through it from 0 flux to now maximum flux. Well, if we keep turning it, 0 flux again. Now a negative flux, because normal would always point the same direction. So let me try to do this. So if the normal's up 0, forward, 0 pointing down on the page, backwards, and then we do it again. So as we change this angle, that would change the flux, which would induce an EMF. And if we have an induced EMF, an induced voltage, we get current flow in that loop. This is a generator. So you plugged things into outlets today, or you used something that was plugged into an outlet or plugged into our electrical grid. And virtually all of our electricity in our electrical grid is generated by some external mechanical force of energy turns a loop in an external magnetic field. And while that loop is turning, so the flux is changing, there is an EMF produced. And we do it at the right rate so that we get a voltage at the wall outlet of 110 volts. So the wall outlet is an induced EMF. It's an induced voltage. It's not big chemical batteries producing voltage like we've been doing for the first part of the whole rest of this semester. All voltages came from batteries, and they were constant in direction. This is an induced EMF, and it will actually change direction, but we'll get to direction later again. So I do want to point out something about this. Most of the time, we're only going to change one thing. So if you have an average change, you would rewrite this equation, and I'm going to go ahead and put absolute value around it. And instead of the derivative symbols, I'm going to use my deltas. So if when I flipped, let me try to get these both back on the screen. When I flipped this coil from here to here, if that's the only part I'm looking at, what's the average voltage? I would use change in flux divided by change in time. So to calculate the flux here, divide by the time it took to get it. If I knew a function, I would actually do the derivative. Now here's a piece of this derivative that I want to put together, so let me turn the page. So if I put these two equations together, EMF is negative d flux dt, that's Faraday's law, and flux is BA cosine theta. So any 3 of these can change. So if I put them together, EMF is negative d dt of BA cosine theta. So we could have a changing magnetic field with a constant area and a constant angle. So you'd have A cosine only dB dt. Or we could have a changing area. That's rare. About the only way you can do a changing area is like if you have a long loop of wire like this, and then you pull the 2 ends. It's going to pull this into a smaller and smaller area. So it can happen. But if we would only do that in a constant magnetic field with the same direction. so area and time. Or we can do it by changing the strength of the magnetic field. Oh no, I already did that. Change the magnetic field, change the area, or we can change the angle. So in that case, B and A are both constant, and we have to take the derivative of this. Now, the derivative of the cosine function would be the sine of theta times how fast you're doing it, d theta dt. Those of you who are not in calculus, don't worry about it. This, again, is the most common way that electricity is generated. We change the angle by turning the loop in a constant magnetic field. So one loop, no area change, constant external magnetic field, change the angle of the loop. So this is most common. But you'll see some problems where we change the magnetic field strength. And I actually already talked about that. I do want to talk about one more thing two more things about this equation before we move on to some examples. First of all of this was for a single loop. If you have multiple loops, sometimes they ask for the total flux, so you would change the flux equation, and you would say NBA cosine theta, and then the EMF induced would be the same amount. Other times you might be asked for the flux on just one, so you would leave it the same way. But then because there are multiple loops, when you do the EMF, you do negative N times d flux dt. You'll see it both ways in different textbooks. The College Board decided not to even deal with it. They don't include it at all. So if you're given multiple loops and you're asked about flux, look carefully to see if it says total flux or flux from just one loop. But then if it has multiple loops, then if you already included it in flux, don't include it again. If you just did the flux for one loop, then make sure you multiply the EMF, because there's going to be a lot more if you have them. Also, units. So EMF is the derivative of flux over time. So flux we know is Webers, time is a second, and we know EMF is voltage. So this is a volt. Really? I want you to do that as the first discussion question for today. So work on that and we'll go over it in class next time. So now we're going to do a couple of example problems. So if you're done, you're good at this, turn it off. I'm going to do 2 example problems, one averaging and one with calculus. So example 1, we are going to have a rectangular loop in a magnetic field that's pointing out of the page. So B out of the page has a value of 0.8 Tesla. This loop has a resistance of 0.1 ohms and an area, I'm just going to skip right ahead to area, 0.1 squared. Please remember, if I give you diameter, that is saying it's a circle, so you're going to do pi r squared. If I give you a square, side squared. If I give you a rectangle, length times width, you know how to calculate the area of shapes. So in this first picture, we can calculate the flux for this loop. So flux equals BA cosine theta. So we have 0.8 Tesla. We have an area of 0.1 meters squared. And the cosine, well, the loop is here, so the normal is either here or the other way, so let's take the one with it just to make life easier. And then, so it's parallel to the field, so this is cosine 0 degrees. So that's 1, and this is 0.08 Webers. So now we're going to turn the loop over 0.4 seconds so that its plane is perpendicular to the page. Well, if we turn this so it's perpendicular, now the magnetic flux is 0. Because the strength of the field is the same, the area is the same, but the angle would be 90 degrees. So this is the original flux, and this is the final flux. So to calculate the EMF, we're going to do, and I want magnitude. All the questions are going to be magnitude. So magnitude, absolute value of negative d theta dt. I wrote M for magnetism. We've been doing B. They're the same thing. Well, I have a particular amount of time, in fact, a pretty big chunk of time. So that's how this is going to turn into absolute value of change in flux over time interval. So absolute value of negative. Final, change is always final minus initial. So 0 minus 0.08 divided by a time of 0.4 seconds. And I don't know if I actually finished this. 0.08 divided by 0.4 is 0.2 volts. And so in this wire, if it was hooked up to a complete circuit, so current could flow, this is trying to make current flow, then I equals V over R. We have 0.2 volts over 0.1 ohms, so we'd get a current of 2 amps over the time that this was turning. One of the things I want to emphasize is that this induced EMF, by physically moving something in a magnetic field, is the exact same EMF. Wow, that was a long bell. Is the exact same EMF as the EMFs we've been getting from batteries. You treat it the exact same way. So if we keep turning it, depending on how much time we turn it over, we're going to continue to get current flow. Now if we stop turning it, if we bring it back here and then stop, we just leave it like this, well then there's no change. And if there's no change, there's no induced EMF. So magnetic field does not make EMF. Change in flux makes EMF. So example number 2, I do want to do a calculus one. So example 2, if I give you a function that the magnetic flux as a function of time was 5t cubed plus 4t squared. So for as time goes from 0 to a bigger number, this is always increasing. We have an increasing flux. Well, an increasing flux is obviously a changing flux. So we can calculate the EMF, negative d flux dt, and here we do want to take the derivative because we have a function. So if you have a function, you take a derivative. If you don't have a function, if you have endpoint numbers, you use the average one with the change, the deltas. So we need an absolute value of negative of the derivative of this. So derivative, remember, you take the exponent, multiply, so 3 times 5 is 15, and drop the power by 1, plus 2 times 4 is 8, 2 minus 1 is 1, we don't usually write that. So we get a negative on both of them, we get an absolute value, so the induced EMF magnitude is 15t squared plus 8t. So if this magnetic flux was possible to continue forever, we would get continuing forever an increasing EMF. We'd have 0 induced voltage at time t equals 0, but then we'd have more and more as we put bigger and bigger numbers for t. So with more and more EMF, we'd get a bigger and bigger current. Now, the last thing I want to point out about the calculus part is that if you have a magnetic flux, some maximum value where then the angle is changing. So this would be like the area of the loop. This would be the area times the magnetic field. And then you're going to turn it. So omega is how fast you're turning it. So if we take the derivative of this, well, let's put it in here. We're going to have negative, this is a constant, so it stays outside. And the derivative of cosine. The derivative of cosine is sine. Excuse me, the derivative of cosine is negative sine, so that makes this positive. And then you've got to multiply by the derivative of the inside. So you multiply this by omega. So interestingly, what this means, this works out, is the EMF is then the EMF max times the sine of omega t. So this says if you're going to turn the loop in order to generate this EMF, in order to generate a current, then you're going to get an EMF that's not constant. It's going to change as a sinusoidal function. So if you do this by changing the loop direction, you're not going to get like a battery voltage. A battery produces direct current. One side is always positive. So direct current, the current always goes one direction. A generator, because it's producing this EMF by turning the coil, changing the angle, generates alternating current. So the current goes this way, and then this way, and then this way, and then this way, and 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 this way. And you can see how that's a sinusoidal curve, essentially. So positive and negative switch at a frequency, and remember this is angular frequency, at the angular frequency that is chosen. So you may have heard these terms before. Direct current is DC, alternating current is AC. Excuse me. So a battery, because it produces current in one direction, runs electrical circuits one particular way. A generator, so all the wall plugs are AC, they're alternating current. The electrons are going one way, then the other way, and then back and forth and back and forth and back and forth. And you saw this in the simulation lab. There's no difference in most contexts what you observe as long as this is fast enough. The lights in this classroom are cycling at 60 hertz. That's how we set up the power system in this country. About half the world, I think, it may be slightly more than that, cycles at 60 hertz. So they turn the coil at 60 hertz in the generator. Or, yeah, that's 60 hertz. Other parts of the world do it at 50 hertz. But both of those are chosen to be high enough that so for lights, for instance, the lights in this classroom have positive, negative, negative, positive, positive, negative, negative, positive. They're turning on and off 120 times a second. But we don't see it because that's too fast for us. So to us, most of the time, AC visually is not any different than DC. If you want to measure it, it makes things change and it makes things more different or more difficult. But we're just going to barely start with an introduction to AC. We're not going very far in it. Okay, so that's enough. I've talked for too long.